Okay, so I'm gonna look at the interference phenomenon. Okay, so it's always the same question. What's the nature of light? We kind of have an idea of it. Is it composed of waves or particles? All indications so far is it's composed of waves. Right?
From the Discovery Channel and ABC News, Discovery Newsbreak.
Good evening, everyone. Astronomers announced today they have found 6 new planets orbiting nearby stars. This brings the total number of planets discovered beyond our solar system to 28. Astronomers find planets by looking for stars that wobble. That unsteadiness is caused by the faint gravity of an orbiting planet pulling on a star. That's Discovery Newsbreak.
Okay, so this was recorded like 20 years ago. Okay, so they discovered what, like less than 30 planets. Back then, now we got like thousands upon thousands of planets. And now we're discovering Earth-like planets. The question is how? How do we even get to see these planets, given the fact that you cannot see these planets directly? They're not the sources of light. They're not like stars. All right, so they kind of reflect light. You can barely see these stars. Forget about being able to see their planets. So how did we know that some of these stars had planets in the first place? We'll get to investigate that.
Angel's novel two-eyed telescope.
Of course, the technology advanced quite a bit, and we're actually able to see quite a bit more than we were able to 20 years ago, obviously.
Maybe the first to analyze directly the faint light of an alien planet. The two mirrors will be yoked together to create history's biggest pair of binoculars. Each mirror will have a slightly different view of a star. The light waves from these two vantage points will be combined to reveal a distant planet's light.
Well, the difficulty with trying to see planets around stars is that they can be 1,000,000 or even 1,000,000,000 times fainter than a star. So any kind of glare from the star spoils your view of the planet. There's a trick to get rid of the starlight and leave the planet light there. And what you can do is combine the waves from the two mirrors so that the crests from the wave from one mirror come at the same time as the troughs from the other. When you add those together, the starlight cancels.
So is it possible to cancel out the starlight so you can see the planet itself?
So in that way you can...
So we'll check to see if that's possible. Take a look at the soap bubble. All these iridescent colors. It's amazing. Where do these colors come from?
The very idea of alien life on alien worlds was once incendiary. In the year 1600, at the Field of Flowers in Rome, a pyre was prepared for a heretic. His name was Giordano Bruno, a philosopher and former monk. Bruno lived only a few years before telescopes were invented. Yet Bruno was convinced that every star had planets, and every planet teemed with life. Didier Queloz was risking his career if he had been incorrect, but Bruno, whether right or wrong, had risked his very life. Imprisoned for 8 years by the Inquisition, he had been begged to recant. On this day, there would be no such offer. Other worlds, a disturbing idea, an idea that must be suppressed. Wasn't Earth a unique creation? Would each of Bruno's worlds have its own Jesus? Pull on one thread of Bruno's thinking, and all of Catholicism seemed to unravel. His writings were declared erroneous, his volumes ordered burned and placed on the index of forbidden books. But Bruno remained defiant. Most criminals were strangled first and later burned in effigy, but Bruno's heresies were so corrosive that he was sentenced to die by flame. The man who dared to say that Earth was not the only world God created now paid the terrible price of his convictions.
Okay, so Bruno had an interesting look on, I was going to say life, but the universe in general. He thought that the stars had planets, and the planets had life, kind of like Earth does. So that becomes the question: is there intelligent life elsewhere in the universe? And then the question becomes: how did life begin in the universe in the first place? Okay, so outside of religion, obviously we don't invoke God or whatever your religious background is, your belief system is. From a scientific perspective, how do you go from Big Bang and energy turning into particles like atoms, and then atoms forming molecules, and then eventually molecules forming cells, and you becoming you and me becoming me, and then we having this discussion? So the question becomes, when you go from molecules into cells, something called consciousness kicks in. Awareness happens. So where does that come from? So what's the origin? What are the origins of life? How does that come about? This question is going to become significant in modern physics, because the modern physics is one of consciousness experience. There are two versions of it, interpretations of quantum theory. The modern physics is quantum theory. And the applications of quantum theory. Just about the most accurate theory ever invented by human beings. Without it, the technology that we're using today would not be possible. We would not, this Zoom meeting would not be possible. A lot of the electronics would not be possible. Quantum theory is highly accurate. At the same time, it's absurd. It's got a lot of quantum weirdnesses. Not very commonsensical, that's what it means. These particles don't usually exist outside of a conscious observer. So the question is consciousness, awareness. Where do we get it from? And whose consciousness is the one which is creating the universe? Because somebody's consciousness is taking these waves, question is waves of what? And turning these waves, question is waves of what? Into the particles that create the universe. And if there's, obviously, there's life here on Earth, the question is, how did that come about? And if it happened randomly, chances are pretty damn good that it must have happened elsewhere in the universe as well. And if it did, where's the evidence? Is it possible that we're being visited by other intelligent beings? 20, 30, 40 years ago, most physicists would have said, yeah, I mean, everyone is open-minded enough to think that there's probably life elsewhere in the universe. Possibility is great. But the question is, even if there's intelligent life elsewhere in the universe, what are the chances that they're going to be able to visit us? All right, as you cannot travel at the light speed or faster, even at the light speed, these nearest planets or whatever, they're light years away. But we can't even travel at the light speed. So even if there's life elsewhere in the universe, how are they going to be able to travel these enormous distances to come and visit us? That was the biggest question. And all of a sudden physics evolved, and then modern physics will say, yeah, it may be possible. Now we're a little bit more open-minded regarding that sort of stuff. What I'm talking about is taking shortcuts through the space and time in a weird sort of way. And so we will actually start getting into that sort of stuff next week.
Tests over the next few weeks revealed an even more puzzling problem. Data from the 94-inch mirror simply didn't make sense. It seemed to indicate that the mirror could not focus. As the evidence mounted, no one was eager to confront the possibility of a major malfunction.
The primary contractor who had built the mirror and the telescope,
Right, we've seen
who was nominated.
Let's move forward with that one. Oh, the problem with this one is, remember the shape of the mirror? Okay, so when they cut the mirror and they just grinded it, and they thought that they had the right shape of the mirror. So how did they know, or what made them think that they have the right shape?
It was Devitt.
All right, so obviously they conducted a bunch of tests. So the question is, how did they know that the mirror had the right spherical shape?
Creating an aircraft able to cruise at Mach 3 was difficult enough, but the Skunk Works also had to face the challenge of combining this level of performance with a new science of stealth. To avoid features that would create strong radar reflections, the plane had taken on a revolutionary shape. The wings were blended into the body, and the long surfaces on the forward fuselage were designed to deflect incoming radar waves. So were the inward angled twin fins, the pointed engine cones, and the nearly flat lower fuselage. Also, they developed a special radar-absorbent plastic, or composite, that was incorporated into all the leading edges.
When you look at an SR-71, 20% of what you see is composite. You know, it's just unbelievable at that time. And it was developed in our shops. An SR-71 was 100 times smaller radar return than an F-14, which is only half as big and was developed 10 years later. So that was a really, truly first airplane specifically designed with stealth in mind.
On December 22nd, 1964, the SR-71 was rolled out onto the flight line at Lockheed's Burbank plant, the Blackbird. Coated in black radar-absorbent ferrite paint, the Blackbird was an extraordinarily futuristic-looking machine.
Okay, so the radar absorption, how does that work? How do they make these airplanes radar invisible? All right, so the nature of light is composed of waves or particles.
They say an apple inspired Newton's law of gravity, but it was actually a comet.
All right, so we've seen this one.
By 1680, Isaac Newton is already renowned for his brilliance. But for the last 10 years, he has retreated into seclusion. He dabbles in alchemy. His work goes unpublished. Then, a spectacular comet appears in the night sky. His genius is reawakened. He emerges from isolation, builds a telescope to study the heavens, and decides to make his ideas public. The result, one of the most brilliant books in the history of science, the Principia. It lays out his revolutionary theory of gravity and the laws of motion. In the words of Alexander Pope, nature's laws lay hid in night. God said, let Newton be, and all was light.
All right, so we discussed that before. So Newton thought that the light was composed of particles, right? Because particles can transfer motion, momentum through collision.
30 years ago, space was considered a
So by looking at the tail of a comet, you know that the tail is composed of dust as well as ice particles, and they're being pushed away from the sun. And so they're being pushed away from the sun by something coming out of the sun. And what's coming out of the sun, as far as he was concerned, was the particles of light. And the particles of light, through collisions, would push the particles making up the tail of a comet away from the sun. All right, only through collisions the motion can be transferred, momentum could be transferred. Thought Newton. He dismissed the idea that the light was composed of waves. All right, so Newton came up with the corpuscular theory, said that light is composed of particles, not waves. All right, so 16 meters. And then he made that assertion based upon the tail of a comet, which is pointing away from the sun. So something from the sun is pushing the tail away from the sun. That's it. Huygens thought that the light was composed of waves because the waves can interfere. They can interfere constructively. As a result, you will end up getting brighter light, or destructively, you can end up getting dimmer light or complete cancellation of light. Which they think
Isaac Newton,
that'll be a complete dark. It'll become complete dark.
who investigated both refraction and dispersion. According to Newton, light was made up of particles that, obeying the law of inertia, traveled through empty space in straight lines. For Newton, refraction, or the bending of light by matter, could be explained by the gravitational attraction between light and matter. However, at about the same time and on the same subject, an opposing viewpoint arose in Holland. Christian Huygens, a Dutch physicist and astronomer, theorized that rather than being composed of particles, or corpuscles as Newton called them, light was made up of waves, and in the long run, his idea would be seen as the correct one.
All right, so 1670s, actually 10 years before Newton, he introduced the wave theory based upon the superposition of waves. We're talking about the interference of waves.
In the early 1670s, Christian Huygens formulated a principle of light waves, stating that every point on a wavefront is a source of new waves. And in 1801, despite the prominence of Newton's rival corpuscular theory, another Englishman, Thomas Young, proved beyond a shadow of a doubt that light is a wave. He accomplished that by proving that light has the wave property called interference. Wave interference can be seen to be constructive or destructive. If the waves, as they travel, encounter each other in step, they can reinforce each other, create a stronger wave, and produce what's known as constructive interference. But when they're out of step, waves can cancel each other completely. In other words, destructive interference. As Thomas Young suspected, all waves in all media behave in this fashion. And to prove that light is a wave, he merely had to illustrate that light exhibits interference, the behavior common to all waves. Here's the principle. Light from a single source enters two slits, which are side by side and not much farther apart than the wavelength of the light itself. After passing through the slits, the light shows up as a distinctive pattern on the screen. When a single plane wave encounters two slits, each slit becomes the source of spreading wave fronts. And because both new waves originate from the same plane wave, their oscillations are synchronized. The result is a stable pattern of up and down ripples, alternating with directions along which the waves cancel one another. This produces a pattern of bright fringes of constructive interference on the screen, separated by dark fringes of destructive interference. And that was it. A series of alternating fringes to prove that light is a wave. It was a conclusive demonstration, and ever since, physicists have had to explain the behavior of light in terms of the properties of waves.
Okay, so double slit experiment proves that the light is composed of waves because you end up getting a fringe pattern on the screen. You got the dark fringes as well as the bright fringes. So the question becomes, what's causing the dark fringes? Fringes are dark because of the absence of light. Okay, so when you have two slits, parallel slits, if anything, you should have only two shadows. You're not supposed to have multiple fringes like that. So, which means that at places where you see dark fringes, you end up getting a destructive interference pattern. If you're looking at the bright fringes, believe it or not, towards the middle of these fringes, it gets brighter. So, which means that you end up getting a perfectly constructive interference pattern. So, at places where you have dark fringes, the interference pattern is destructive. at places where you have bright fringes, you got the constructive interference pattern, only the waves can interfere. So what that means is the light is composed of waves. So the debate is settled. All right, so the nature of light is one of waves. Waves will interfere constructively as well as destructively. Constructive interference is going to be bright fringes, destructive interference is going to be bright fringes. All right, so according to Huygens' principle, and the video was trying to explain it, every point on a wave is going to behave as a source of a new wave. All right, so that's end up getting an interference band. Every single point on a wave is going to act like a source of a new wave. All right, so the interference is going to be the property of the wave phenomenon, so which means that it's going to be the light waves, sound waves, water waves. So, yeah, so it's going to be all of these. All right, so here's the picture so far regarding the nature of light. Newton says composed of particles. Huygens says composed of waves. Young's double slit experiment gives you an interference pattern, otherwise known as the diffraction pattern. You have the bright as well as the dark fringes. Dark fringes form because of the destructive interference of light waves, and the bright fringes are formed because of the constructive interference of light waves. Light waves, not the rays. All right, so that's the conclusive proof that the light is composed of waves, not particles. Okay, so let's just step through this a little more mathematically, okay, because some of you guys are getting into things which are slightly technical, so it's not a big deal. A couple of things that we will have to focus on from a mathematical perspective. So S1 and S2 is going to represent the sources. This is slit number 1, this is slit number 2. D represents the separation distance between these two slits. So it's a double slit experiment, so you got 2 slits as a result. All right, so you got a light ray moving this direction. It's a wave, but this, if you think of it in terms of a ray, this is the direction that the wave is going to be traveling. All right, and then it's causing an interference pattern on the screen. So the screen is located right here. You see the interference pattern on the screen. All right, all right, so here's the angle of diffraction that you're looking at, whatever that is, we'll discuss it. So the light is moving at an angle with respect to the vertical or the normal. All right, so this angle is the same as this angle that you're looking at. Okay, so delta L is going to represent the difference in length. All right, so if you're looking at this slit and where the interference pattern is forming for this particular wave, all right, so this is going to be that length that you're interested in, and this is the length to the screen at the same angle that you're looking at. But when these waves interfere, obviously, this is going to be at this angle, this is going to be slightly bigger or smaller, it doesn't matter. So there's going to be a length difference between this wave and that wave that we're going to be looking at. All right, so whatever this angle is, that angle is going to be exactly the same as this angle here. All right, so you make a small triangle as a result. All right, so you draw a line, which is going to be perpendicular to these two parallel lines. I'm saying parallel lines, but in reality, they're not 100% parallel. All right, there's going to be a slight angular deviation between these two, and then the reason is going to become obvious shortly. All right, so this angle is the same as this angle, almost the same as that angle. Delta L is going to represent the length difference to the screen relative to these slits that you're looking at, and D is the separation distance between these two slits. All right, so which means that this wave and that wave, they will interfere on the screen, and they will form an interference pattern. All right, they're almost parallel, but remember, separation distance between the slits is going to be relatively small compared to the distance to the screen. So the angular deviation from the normal is almost the same, but they will cause an interference pattern right on the screen. All right, so I already explained this to you guys, and then interference pattern is going to look like that due to those waves coming out almost at the same angle. That's what it means. All right, so now set up the mathematics a little bit. So first slit to second slit. All right, so these are also the light sources that you're looking at. All right, so you got two waves which are parallel to each other, almost. All right, and so this represents the normal. separation distance between the slits. And where this line is going to be the distance between these two parallel waves. All right, so these waves will not have the same length to the point of interference that we will be looking at. So there's going to be a little bit of a length difference. All right, so L2 is going to be slightly longer than L1. So the length difference is known as the path difference. Okay, so obviously we are making a small triangle there. All right, so I'm going to place the angle right there. So D is the separation distance, and L is going to be the length difference between two interfering waves. Now for the constructive interference, all right, so the length difference should be the multiples of a single wavelength. This is known as a phase difference in a sense. But the length difference between the length of the first wave and the second wave has to be the multiples of a single wavelength. If there are multiples of a single wavelength, it's going to cause a constructive interference. All right. So as long as delta L is going to be multiples of a single wavelength, you're going to end up getting a constructive interference. That's what it means. All right. So delta L is going to be the multiples of a single wavelength. It could be one single wavelength. It could be 2. It could be 10. It could be 20. It doesn't matter. As long as it's exactly a one multiples of a single wavelength, you will end up getting a constructive interference pattern. So do a back substitution. N could be 1, 2, 3. Like I said, the multiples of a single wavelength is the way to do it. So that's going to give you a constructive interference. So this becomes the formula for the constructive interference. For the destructive interference, the length difference has to be multiples of a half a wavelength. If these waves are off by half a wavelength, it's going to give you a destructive interference pattern, which means that the trough of one wave is going to coincide with the top of one wave is going to coincide with the bottom of the other wave. So that gives you a destructive interference pattern. And it can happen only if you have multiples of half a wavelength. So instead of saying multiples of half a wavelength, this is what we will get to do. All right, so you got your one half a wavelength, and then you can do multiples of it. So you can make this 1, 2, 3. As a result, the difference is always going to be half a wavelength in essence. All right, so this is going to give you a destructive interference pattern. I noticed that this starts with n equals 1. This starts with n equals 0. All right, so if n is 0, obviously it's going to give you the length difference, the path difference, which is going to be only half a wavelength. Okay, so those are the main formulas that we will get to use. Okay, so the question is, so what? And what does it mean? You got sine of theta, and then we got a bunch of conditions regarding what causes a constructive or destructive interference pattern. Okay, so which means that we need to come up with some little bit more commonsensical at this point. Okay, so this delta means difference. Okay, so delta is going to represent the difference in length, difference in the path length that we were dealing with. All right, so notice that you got two rays which are almost parallel to each other when they're emerging from these slits. They're forming the interference pattern. If the path difference is multiples of a single wavelength, this is going to give you a constructive interference. If it's a multiples of a half a wavelength, it's going to give you a destructive interference. So that's what we were discussing. All right, and L is going to represent the distance to the screen. And then we got the two additional letters. One of them is L, the other one is the letter Y. All right, so letter Y is going to be the distance with respect to the center that you're looking at to the interference pattern that you're looking at. It's either a constructive interference pattern or a destructive interference pattern. So it's either a bright fringe or a dark fringe. Okay, so that's just going to give you the distance regarding that. All right, so continue with the derivation. It's because I'm going to come up with one single mathematical expression for this one. So these, once again, the separation distance between the slits. All right, so what else do we have? This delta that you're looking at is going to be the path difference. Okay, we're using delta L for that. It's the same thing. R2 is going to be larger than R1. So capital L is the distance to the screen where the fringe pattern is going to form. Okay, so the letter Y is going to represent the distance from the center to the fringe pattern that we're interested in. So it's going to be distance between the bright fringe, which is right at the center, the central bright fringe, which is going to be right at the center. Distance between the bright fringes and the central fringe, whatever that is. Okay, so the central fringe is going to be right at the center. All right, so evidently we're looking for an expression for the distance between the bright fringes and the central fringe. Okay, so it's going to be a constructive interference pattern, if that's the case. All right, so if we're looking at the distance between bright fringes and the central fringe, okay, so which means that delta path difference that we're looking at is going to be the multiples of a single wavelength. This has to be the multiples of a single wavelength. That's what it means. All right, so we will get to express the path difference in terms of the separation distance between the slits for a constructive interference pattern. So this is the hypotenuse, this is the base. So sine of the angle is going to give you the path difference over the separation distance. Path difference for constructive interference is going to be multiples of a single wavelength divided by separation distance. All right, except the problem is obviously we're not going to be able to measure this angle because this angular deviation is extremely small. In real life, you cannot measure the path difference between this and that. A path difference is going to be multiples of a wavelength. There's no way you can measure something like that. That's way too small. So which means that we have to come up with measurables which are measurable. Yeah, that was a key thing to say. Which means that you have to come up with things that you can directly measure using a measuring stick of some sort. Okay, you cannot measure things in terms of nanometers. It's not going to make sense. You need to have a microscope to measure something. We can measure the distance to the screen, obviously, and we can also measure the distance to these fringe patterns. So whatever it is that we came up with here, in theory, the stuff that looks good on paper does not work in real life. So which means that this stuff needs to get translated to something that we can use in real life. So we need to express this cute little idea, mathematical idea that looks good on paper, to something that we can measure. All right, so slit separation, you can measure. There's no question about it. The path difference expressed in terms of multiples of a wavelength, good luck. All right, okay, we're physicists, we're not mathematicians. So which means that whenever you come up with an idea like that, you have to kind of keep developing the formulation until it gives you something that you can measure. All right, so what do we do? Now we will have to express this idea in terms of things that we can measure. I can measure the distance to the screen. I also can measure the distances of the fringes relative to the central fringe. Okay, this is measurable, this is measurable. So I want to take this idea and express it in terms of something that I can measure. So I'm going to make one more triangle. All right, so this theta is the same as the other theta, as I know. And this time you got the hypotenuse here. This would be the length of the wave, light wave, moving in that direction, which is going to cause an interference pattern. Okay, and this one is tough to measure. This is the hypotenuse, but I can measure this distance, the length, and I can also measure the distance between the bright fringes and the central fringe. So it's going to be the opposite over the adjacent. So that's going to be the tangent of the angle. All right, so how do you take the tangent of the angle and relate it to the sine of the angle? Becomes the question. All right, so for that purpose, we end up using a little bit of trig. All right, so tangent of this angle can be expressed in terms of sine of the angle divided by the cosine of the angle. All right, and then it gets kind of interesting. So I'm trying to be right. There's something called the small angle approximation. All right, according to the small angle approximation, if this theta is very small, it's not zero, but it's very close to zero, and so which means that you're looking at a number which is very close to zero. The sine of a number which is very close to zero is going to be theta, and the cosine of a number which is very close to zero is going to be 1 in essence. All right, so this is called a small angle approximation. So which means that the tangent of theta expressed in terms of sine of theta and cosine of theta, this cosine of theta is going to be roughly about 1, and tangent of theta is just going to be the angle that you're looking at. All right, so what that means is tangent of theta and the sine of theta can be thought of the same thing, as long as it's a very small angle approximation. So the sine of theta and cosine, the tangent of theta, can be thought of the same thing in essence. All right, so this is going to be the same as this. So instead of using, all right, so which means that the sine of theta expression, and this is what you got on the right-hand side, and the cosine, the tangent of theta expression, which is this on the right-hand side, this allows you to be able to equate those to each other in essence. All right, this, I don't like the way I did that. It's just something looks kind of fishy. Idea is still the same. So in this small angular approximation, tangent of theta is the same as sine of theta. All right, just go with it. All right, so this is known as a small angular approximation. Okay, now we can express everything in terms of measurables. All right, so this is the final formula that you come up with. The only thing you're going to be responsible for is this final formula, and then we will take a look at a few applications of it. All right, so what does it mean? What's the meaning of it? So the n is going to represent the order of the fringe that you're looking at. The central fringe is obviously it's going to be, what is it? It's going to be 1, I think. And if you're looking at central fringe, is probably going to be 0. I'm just trying to think of, yeah, central fringe is going to be 0 because there's no deviation with respect to central fringe. Okay, so y represents the distance of bright fringes relative to the central fringe. All right, and what else? The first order bright fringe is going to be 1. The second order is going to be 2, and so forth. All right, so what is it that you could do with this, which is real neat? guys, the only thing that you could do with this formula, remember we were talking about the wavelengths of different colors. Remember, red has the largest wavelength, and there's a number next to it. And obviously, violet is the smallest wavelength. There's a number next to it. Okay, so how do you measure the wavelengths? This is how you do it. So if you do a double slit experiment, believe it or not, you're going to see fringe patterns. All right, normally you would see dark and bright fringes. But then again, depending upon your light source, if your light source is all the colors that you're looking at, notice that you will have bright fringes forming at different places. All right. And as a result, you can just measure the distance between the bright fringe that you're looking at, whatever the color is, to the central fringe. Check to see if you're looking at the first order term, the second order term, or whatnot. You know the separation distance between the slits. You know the distance to the screen. From that, you can figure out the wavelength of the color that you're looking at. This is real neat. This is one way you can figure out the wavelength. All right, so Young's double slit experiment, when expressed mathematically, you know, it's kind of involved. I get that, but it's got some amazing applications. Okay, let me check to see if I have the solution for it first, because if I don't have the solution, guys, this is the last thing that I'm going to do. We will continue this next week, obviously. All right, this week was too much lecturing. Okay, so in this case, red light is being used instead of white light. You have to just pick and choose. Red light, more than likely it's laser, or red light in general. It's red light. Okay, for the double slit experiment. Okay, so you don't get some kind of something that looks like a dispersion. All right, so the slit separation is given. Slit separation is very small, 10 to the minus 4 meters. That's in terms of millimeters. And then the screen distance is about 3 meters. This is almost like we're looking at something about almost 10 feet away. All right, so what are we looking at? We're looking at the distance along the vertical direction on the screen between the central bright fringe, which is right here, and the third order bright fringe. So this is the distance that we're looking at. All right, so everything is given. So figure out what this distance is for the red light, in essence. All right. From now on, what I want to do is I want to give you guys multiple choice math problems. I'm going to give you guys 5 from now, because I want you guys to focus on using the formulas. I'm not interested in seeing work. Just understand the basic formulas and be able to use them. All right, this is much easier than what I was expecting from you guys previously, because I'm not interested in the math. Also, the problems are kind of straightforward. Okay, that's the reason why I'm putting the emphasis on the formulas at this point. Don't worry about the derivation, but understand the meaning of the formula that we just came up with. All right, that formula in real life would be used to figure out the wavelength, because everything else is measurable. These are book problems. Obviously, I don't like the book problems for the obvious reason, because, you know, who cares? You can calculate the distance between two bright fringes. I can measure that. So there's not much reason of calculating something that you're going to be able to measure. It's much more interesting to actually figure out the wavelength of the light source that you're using. Anyway, so So red light is the expressed in terms of nanometers, 10 to minus 9. That's the meaning of nanometers. Separation distance between the slits. This is what you get in terms of meters. Distance to the, all right, this is the distance to the screen expressed in terms of meters. So what is the distance between the bright fringe, between the third bright fringe and then the central fringe? I need coffee. All right, so in this case, M is going to be 3. I'm using M3. M is the same as N. Evidently, I keep changing notations. All right, that's fine. All right, M should be the same as N. I don't know why I did that. Okay, so the first thing I'm going to do is just figure out the angle using this formula, and then apply it to this formula. All right, so instead of using a small angle approximation, the stuff that I was talking about, I'm just going to brute force it. Okay, so figure out the angle. And once I figure out the angle, now I can figure out the length along the y direction. If I know the distance to the screen. All right, so just do a substitution into that. All right, and then this is going to work the same ways, and then plug the numbers in. Instead of the small angle approximation, I decided to keep this sine of theta and then isolated theta, and that theta gets substituted into the theta of tangent. And then I got my measurables, and it's going to be 3. I've got the wavelength. I know the separation distance between the slits. I know the distance to the screen. Plug the numbers in, and that's the number that you come up with. All right, so that's it. Okay. Fringe pattern on the screen. It's going to look like this. So we're looking at the fringe pattern. One of the things that I want you to notice is you got the dark fringes, you got the bright fringes. And when you're looking at the bright fringes, the central one is the brightest. And then it starts to get dimmer and dimmer and dimmer and dimmer. Not every single fringe is going to have the same brightness. That's number one. Number two thing that we notice when you're looking at a fringe pattern is it doesn't matter which fringe you're looking at, it's going to be the brightest at the center. Towards the edges, the fringes become dimmer. All right. So the question becomes, how come the central one is the brightest and the other ones are not quite bright? And why is that it's the brightest at the center and towards the edges it gets dimmer? All right, so this is known as the intensity distribution. So we're going to be looking at the intensity of light for each and every single fringe. All right, so you got the central fringe. This is going to be the brightest. The intensity is represented by this curve. Notice that's going to be taller than any other curve. It's going to be brightest at the center, so it peaks. Gradually becomes darker, and then it peaks again. Gradually becomes darker. At the peaks, it's going to be the darkest. But notice that as you start to move away from the central fringe, it's the brightness starts to diminish. So they're not as bright. All right, so brightest, and then it starts to get dimmer towards the edges. All right, so how do we explain that? Well, obviously we're going to get to explain it using the interference pattern. Is the way to explain it. All right. So here's the intensity of light. We came up with this formula a couple of weeks ago when we were dealing with the electromagnetic waves. All right, so this is the RMS value of the maximum. This is the electric field amplitude that you're looking at, the RMS value of it. So when you square that and then multiply it by these two constants, this is the speed of light. It's going to give you the intensity of light expressed in terms of the electric field components. So we got two slits, S1 and S2. So these are our light sources. All right, so what's happening is the electric field from the first slit, all right, this is the maximum amplitude that it's got. It's going to be expressed in terms of the sine wave, omega t. Omega is an angular frequency. What this means is the electric field is just going up and down. It's just vibrating up and down. It's undulating. Okay, not only its value is changing, but it's obviously its direction is changing. So it's like a sine wave. It just goes up and down. It's traveling at the light speed. And likewise, here's the electric field from the second source. It's doing the same thing, except these two waves are out of phase by this much, which means that when you put the waves on top of each other, one of them is slightly in front of the other one by this much. Okay, so they're not exactly 100% coincident on top of each other. This is known as the phase angle, which means that if there's a phase angle, they're not quite, one of them is slightly in front of the other one. Or if its phase angle is 0, they would be exactly on top of each other. All right, if the phase angle is 180 degrees, then one wave would be 180, one wavelength, one half wavelength in front of the other one. So you would end up getting a destructive interference pattern. All right, so what we do, just add up, let's come up with a total wave. So these waves will interfere in space, so which means that you can add them up. So this plus that, they will be added to each other. It's the sine wave, so it's this one. This is slightly in front of the other one or behind this one by this angle. All right, so now for us to be able to add up these waves, okay, so we have to use a trig identity. So sine of alpha plus sine of beta can be expressed in terms of 2 times sine 1/2 of this angle plus that angle times cosine of 1/2 this angle minus that angle. All right, so this is the expression that we end up using. This is known as a trig identity. All right, so this equation is going to be expressed using this trig identity. Man, this is going to be a lot of fun. All right, so this plus that for sine of 1/2. And then we have cosine of 1/2, so it's going to be this minus that term. Okay, let's stop at this point. All right, so this plus that is going to be 2 times omega t, and here omega t's will cancel. All right, this is good. All right, so cosine of a negative angle is going to be positive. All right, so this is going to be positive. And then we have to distribute this into this parentheses, so 2's will cancel. So this is going to be phi or phi divided by 2 right there. Okay, all right, so this is good. So this is going to be positive. So this is going to be phi, cosine of phi divided by 4. All right, come on, let's go, let's go. I don't know, something I didn't like. That's fine. Oh, what did I do? Oh, okay, that's fine. Okay, yeah, there was a mistake there. I made a correction. Okay, cool. Now it makes sense. All right, so this negative term is going to be a positive term. And that's as far as this is going to go. Let me check to see what this means. All right, so this is the undulating term, sine wave. So this thing is going to be going up and down, up and down. It's still moving at the light speed. This is the resultant wave. Remember, when you add up the waves, you end up getting a resultant wave. All right, so this is your resultant wave that you're looking at. Here's the maximum amplitude of the electric field. It's going to be going up and down. All right, so this term is going to affect the maximum amplitude. So now this becomes the maximum amplitude of the resultant wave. And this is what the wave is doing. It's still undulating in space. All right, so this is known as the maximum amplitude term that you're looking at. And with that maximum amplitude term, bam, bam, bam. Okay, now let's come up with an expression for the intensity. All right, so this E is going to be the same as that E. All right, so, okay, this whole expression is squared. And that's, all right, this is the maximum. Okay, so we have to do an RMS expression. This is the maximum amplitude. We're given the RMS expression. So RMS expression needs to be expressed in terms of the maximum amplitude. Okay, and then, okay, I gotta stop here just briefly, check to see what is going on. All right, so this substitute in here. So 1 over square root of 2 squared is going to 1/2. Our C is going to be there. This is not going to change. So this term becomes the maximum amplitude squared. All right, so this is the maximum amplitude squared. Okay, this term is actually the same as this term. All right, I should have not used this term here. Okay, wait a minute. No, that's fine. This is the maximum amplitude squared. This is maximum amplitude is this one. All right, so this needs to get plugged into this one. It goes in there. All right. And then we end up coming up with an expression that looks like this. All right, so 4 and 2, you get a cancellation, so it's going to be 2 here. Everything else is fine. All right, so this expression that you're looking at, you got the amplitude. This is the maximum amplitude that it can have. You got a constant. C is a constant. 2 is a number. So this entire expression could be taken to be your maximum intensity. All right, so this becomes your maximum intensity, otherwise known as the intensity amplitude. And then, all right, so this is the expression that we end up getting. All right, so this is the maximum amplitude, maximum intensity that this is the maximum intensity that you're looking at is going to depend on the phase difference between 2 waves that you're looking at. That's the meaning of it. All right, if you were not able to follow this, it's not a big deal. All right, this is intended for a little bit more advanced lecture. I'm just trying to figure out an expression that we will get to use. There's a formula that I'm trying to get to. All right, expressing this phase angle in terms of the difference in path lengths divided by the wavelength. All right, so that's the expression that we will get to use. So do a back substitution to that one. All right, 2's will cancel, obviously. All right, let me check to see if this is the final expression. All right, there's a square here. There has to be a square there that I kind of skipped. Oh, listen, hopefully I'll notice that. All right, so tangent of theta roughly about the same as sine of theta. All right, and so in terms of tangent, it's going to be opposite over d, which is the same as y over L if there's a screen. All right, the path difference can be expressed in terms of that geometry. Okay, finally, I noticed that the square is missing. All right, this is happening during the lecture, obviously. All right, here's the final formula. Okay, finally, we came up with the final formula. All right, let's focus on the meaning of the final formula. All right, so this final formula that you're looking at is going to give you the intensity of the bright fringe that you're looking at. SO represents the maximum intensity, so this is the brightest intensity that you can have. And then what's going to happen is that intensity is going to change depending upon a number of things. All right, how much the intensity changes depends on the location of the screen. This is the distance to the screen. The larger the distance is, the smaller the intensity is going to be, so it's not going to be as bright. It's going to depend on the separation distance between the slits, which is d. All right. So larger the separation distance is, the larger the intensity is going to be. Also, it also depends on the location of the fringe that you're looking at relative to the central fringe. All right. So which means that the further away you are from the central fringe, smaller the intensity is going to become. But that's just all right, let's just take a look at one single problem to figure this out. Okay, so what are we looking at? We're looking at the intensity on the screen at a certain point in a double slit experiment. So the double slit interference pattern is going to be 64% of its maximum value at that point, whatever the point is. So it's going to be 64% of its maximum value. So what is the minimum phase difference in radiance between the sources? What minimum phase difference in radiance between the sources produces this result? So we've got to look at the phase difference between 2 waves and what is the minimum phase difference. All right, so express this phase as a path difference for, all right, so this is the wavelength of the light source we're looking at. It's expressed in terms of nanometers. Nanometers 10 to minus 9 meters. All right, so this is problem number 3 from the handout. All right, so the intensity that you're looking at is 64% of the maximum value. SO is the maximum value, so it's the ratio is 0.64. That's what it means. So what's the phase difference between two waves from two different slits in terms of radiance? All right, so here's the formula that we will get to use. Solve for phi or phi. All right, so we know the ratio between those two. All right, so get rid of the square by taking the square root of both sides. And this was fairly straightforward. You didn't have to do too much of a derivation for this one, and then just plug the numbers in. All right, if there's a multiple choice question, I think it's probably going to be around this difficulty. All right, so what do we have? You get the answer in terms of degrees, and then make sure that you convert it to radians. All right, 2 pi radians is going to be 360 degrees. All right, so here's the wavelength of the light source in terms of nanometers. So what is the path length, the path difference? All right, so the path difference in terms of wavelength is the same as the phase difference in terms of 2 pi radians. There's another formula, basic formula, plug the numbers in. And so that's the path difference. All right, we didn't have to use that. We didn't have to use that complicated formula. All right, let's take a look at problem number 4. Okay, so slit separation is in terms of millimeters. And there's going to be an interference pattern on the screen. This is the distance to the screen. And here's the wavelength of the light source. So calculate the friction of the maximum intensity, 0.6 centimeters above the central maximum. So this will be L. All right, let's check to see if this requires anything sophisticated. All right, so separation distance between the slits, millimeters, is going to be 10 to minus 3 meters. Distance to the screen is going to be 80 centimeters. So 1 meter is going to have 100 centimeters in it. So just move the decimal in front of 8 in order to get meters. Source of the wavelength of the light source, expressed in terms of nanometers. Nano is 10 to minus 9 meters. All right, what else do we know? All right, so the ratio of the intensity relative to the maximum intensity, if you're looking at the intensity, which is 0.6 centimeters above the central fringe, so it's going to 0.06 meters. All right, so once again, we will use this. Okay, so I didn't have to do that weird long ass derivation. I didn't have to just use the basic formulas for these ones. All right, so here's the basic intensity formula, expressed in terms of the phase angle or phase difference between two waves. Wavelength, the path difference expressed in terms of the wavelength, or length difference expressed in terms of the wavelength, and the phase difference is expressed in terms of 2 pi radians. So that's a standard way of doing it. So phase angle could be expressed in terms of the path difference as well as the wavelength. 2's will cancel out. And okay, what are we solving for? All right, S, we were S now. All right, that's what we're looking for. All right, so this is the difference in path lengths, and this is the separation distance. I don't know why I keep forgetting the square. The square should be there. All right, so from here we can figure out the angle, and this distance, this angle is also the same. This angle is the same as this angle. This is the distance to the screen, and D is the distance between the central fringe and fringe that you're looking at. For a small angle, sine of theta is the same as the cosine of theta. So this is going to equal to that. And solve for the difference in path length. So that's going to get something into that. Okay, so there's still a square here. Okay, so I caught on. All right, and so now plug the numbers into this one. I think this is the formula that we had before. Or just use this formula, I don't care. The long derivation gave us this formula. And now plug the numbers in and you're done. All right, that's it. Mathematically, that's it. Just know how to use those basic equations. All right, so we talked about Maxwell. We talked about Maxwell's equations, obviously. And this is what Gauss came up with. So according to Gauss, this is the Gauss law. Electric field is generated by the net charge within the Gaussian region. And so the net charge is responsible for the electric field within the Gaussian region. There's no net magnetic charge. That's the reason why this is 0. All right. And if you vary the magnetic flux, any variation of the magnetic flux is going to cause a circulating electric field. And this statement says if there's current, it's going to cause a circulating magnetic field around it. This is what Ørsted came up with. And Faraday was thinking, wait a minute, he said, as far as Faraday was concerned, if you vary the magnetic flux, obviously it causes circulating current. What's causing the circulating current is this circulating electric field. And he thought that if you vary the electric flux, it will cause a circulating magnetic field as well. So if you vary the strength of the magnetic field, it's going to cause a circulating electric field. If you vary the strength of the electric field, it's going to cause a circulating magnetic field. Of course, Maxwell is the one who was able to formulate the Faraday's law. This is this, and what Faraday was thinking, which is this. And these two combinations, this and that, give us the electromagnetic waves. So if you vary the strength of the electric field, it causes a circulating magnetic field. Notice that it's just wrapping itself around the electric field. If you vary the strength of the magnetic field, it's going to cause a circulating electric field. The electric field is wrapping itself around the magnetic field. And this field would be traveling at the light speed. What you're looking at is the electromagnetic waves. All right, so inspired by Faraday's ideas, Maxwell formulated the math, publishes it in 1865, notices that all electromagnetic waves travel at the light speed relative to this particular point P that you're looking at. Gets all excited. And that, obviously, the light travels at the light speed, so light is also an electromagnetic wave, just like Faraday was thinking. Except the problem is, if light is a wave, what determines how fast the wave travels is the medium itself. Okay, we already established that. Sound at room temperature travels at 773 miles per hour. Guys. Travels 4 times faster than water, more than 17 times faster than steel. It's the same sound. Why is it that it's traveling faster than water? Why is it that it's traveling even faster than steel? Because the medium itself is what sets the speed of a wave. Wave is a traveling disturbance, and it needs a medium to disturb. While the light travels at the light speed in a vacuum of space. So what is the medium that it disturbs, given the fact that we cannot see any medium that it can potentially disturb? And because of that, the physicists came up with this hypothetical medium that they refer to as ether. And that's the medium relative to which the light is going to travel at the light speed. All right, so because relative to something, you travel at a given speed. All right, so light is going to travel at the light speed relative to this point P. The medium that it disturbs is ether. It travels at the light speed relative to ether, and relative to ether only. That's what it means. So there is a hypothetical medium within which the light travels at the light speed. And this hypothetical medium is a stationary medium. Only relative to this medium, the light travels at the light speed. All right, so that was the understanding that the physicists had. So the question is there ether? All right, 7:31, take a break for 10. All right, so let's talk about the ether theory briefly. Okay, so everything is based upon the definition of a wave. You know that the wave is a traveling disturbance, so which means that it requires a medium to disturb. And then while it's traveling, obviously it's going to be carrying energy with it. All right, the physics of hell. All right, so the question is, what is the medium that it needs to disturb so that it can travel at the light speed? Okay, so a couple of things about it. For it to be able to travel at the light speed, okay, just ignore that one for now. Let's get back to it just for the hell of it. Speaking of hell, evidently I came up with this one years ago to figure out the temperature in hell, and if there's such a place. Obviously, hold on, let me just hide this one briefly. All right, so it's a bit of a thought experiment. So imagine that hell is the hottest place in the universe, right? And then it's a concept that the Western religions have, all three of them. Obviously, if you're not a good enough person, you may end up finding yourself in hell. And then so I decided to come up with some kind of a hypothetical hell where everything is going to be the same. And then obviously you're going to be able to yell and scream in pain. It's going to be a hot place. It's going to be the hottest place in the universe. And it's going to be so hot, in fact, that the sound is going to travel at the light speed. All right, so which means that you can set a hypothetical maximum speed, so how fast the sound can travel. And this also sets the maximum limit to temperature. Absolute zero is as low as the temperatures can get. Also, there's a maximum temperature limit. At the maximum temperature limit, the sound is going to travel at the light speed. That's what it is. All right, so here's the equation that tells you how fast the sound travels. How fast the sound travels is going to be directly proportional to temperature that you're looking at. So hotter this gets, the faster the sound is going to travel. That's what it means. And at the maximum possible temperature, the sound is going to travel at the light speed. Now, how fast the sound travels, how fast the wave travels, also depends on the characteristics of the medium. All right, so B is known as the bulk modulus. It tells you how, it's going to tell you something about the tension of the medium, how rigid the medium is going to be. All right, so this is known as the bulk modulus. And then how fast it's going to travel is going to be inversely proportional to the density of the medium. Okay, so we need to come up with a medium, which is going to have an extremely large tension. It needs to be extremely rigid. That's what it means. And it needs to have a fairly small density. All right, how the more rigid the space is that you're looking at, the faster the sound is going to travel, and lower the density is, the faster it's going to travel. All right, so within these characteristics, I know here's the bulk modulus of steel, which is 1/10 of a trillion. All right, so this is how rigid the steel is. This is the stiffness and rigidness of steel. And by using that, if there's such a place as hell, which is made up of air molecules per se, the air needs to be so rigid so that the sound could travel at the light speed. And this is the bulk modulus of hell. And then notice that it's going to be 10 to the 17 times more rigid than steel will have to be. All right, so which means that if you're trying to come up with a hypothetical material like ether so that the light can travel through ether at the light speed, the ether needs to be extremely rigid. That's what it means. It needs to be, I don't know, 1 trillion times more rigid than steel. And that it needs to have a density which is almost non-existent so that you can actually go through it without noticing it. And that only light is going to be able to experience it. And all of a sudden, you got this weirdness that comes out of physics. So is there such a medium as ether, a hypothetical medium, relative to which the light can travel at the light speed? So that becomes the question. Once again, Maxwell is the one who goes along with the suggestion that there's ether, because the light needs to have a medium to disturb. And Christian Huygens is the one who proposed it. And Maxwell goes, yeah, that makes sense. But the whole thing about ether is, number one, needs to be rigid enough so that the disturbance, electromagnetic wave disturbance, can travel at the light speed. And it needs to have a density, just right amount of density for it to travel at the light speed. Yeah, it has to be such that it's there, light is going to be able to experience it, but we won't be able to notice it. All right, so that becomes really, really weird. All right, so the physicists obviously decided to look for ether. And they started conducting experiments. The biggest experiment was conducted in 1887 here in the United States. 1887.
1887. 1887, the time of Victoria, Queen of England and Empress of India. London is the world capital of commerce. Across the Channel in Germany, a child named Albert Einstein celebrates his 8th birthday. It's been 23 years since James Clerk Maxwell stated his equations for electromagnetic radiation. Beyond the Atlantic, the Americans have enjoyed more than 2 decades of peace and prosperity since their terrible Civil War drew to a close. Waves of migrants from Europe are swelling the population of the United States. The western frontier is being settled and settling down. Looking back, 1887 seems like a time of tranquility, not only in commerce and politics, but also in science. Many physicists believed that all the great discoveries had been made. Physics had reached a state of perfection that was positively ethereal. In fact, the concept of the ether was one of its central tenets. And in 1887, in Cleveland, Ohio, 2 physicists, Albert Abraham Michelson and Edward W. Morley, were preparing an experiment designed to prove once and for all that the ether really existed. Certainly, the ether really had existed, at least in the minds of philosophers, for thousands of years. Today, we can really accept the idea of space as a vacuum, vast stretches of the cosmos that are virtually devoid of matter. But to the ancients, the concept of a perfect void was impossible to grasp. Space had to be filled with something, they thought, and the solution that Aristotle devised was the ether. That was the substance that filled what would otherwise be empty space. And by the 19th century, the ether had come to serve more than a merely philosophical need. The ether was the medium through which light waves from the sun would propagate to nourish and illuminate the earth.
Waves can propagate along the surface of water, or through the body of a crystal, or through the air of a concert hall. But any wave is a disturbance that passes through a medium from one part to another on down the line. In other words, whenever there's a wave, something must be waving. But when light waves from the sun reach the Earth through apparently empty space, what's waving? In the 19th century, the answer was as clear as space itself. It was the ether. To 19th century physicists, the ether was not only real, it had physical properties that could be deduced by observing its behavior. For example, the speed of any wave depends on the stiffness of the medium through which it passes. And of course, the speed of light is enormous. So, the ether must be very stiff indeed. In fact, physicists said, it was nearly impossible to compress it at all. On the other hand, the Earth and other planets moved through the incompressible ether with perfect ease, obeying Newton's laws as if they weren't passing through any medium at all. If the ether behaved like a viscous fluid, the orbiting planets would gradually lose energy and spiral inward towards the sun. And since that certainly didn't seem to be happening, physicists were able to reach another definite conclusion about the ether. The ether, they said, was a perfectly mobile fluid with no viscosity at all. It was a transparent, perfectly non-viscous, incompressible fluid that filled all of space. Knowing so much about it, the only job that remained was to demonstrate its existence directly, in a clear and irrefutable experiment. Somehow, that job had eluded the grasp of physicists throughout the century. But in 1887, Albert Michelson, with the help of his friend Edward Morley, had devised an experiment that couldn't fail.
All right, so 1887, Michelson-Morley experiment.
So in 1887, Michelson asked his friend Morley to work with him on a new and highly sensitive interferometer.
By the way, guys, this is the experiment that put the United States on the map, believe it or not. The United States was kind of like the backwaters of physics at the time. It's kind of like soccer in the United States. No one would take the United States seriously. So the United States wasn't taken seriously until this experiment.
The new interferometer was 10 times more sensitive than his 1880 instrument. Michelson had been thinking of ways to make the interferometer steady and not susceptible to passing carts and people. The mirrors rested on an enormous base of sandstone that floated in a pool of mercury. When Michelson and Morley tested the new interferometer, they were thrilled and delighted. The instrument had all the stability and sensitivity they had hoped for, and should be able easily to detect the tiny expected difference in travel time of the two beams of light due to motion through the ether. The actual experiment was to be done by observing the interference pattern with the interferometer in one orientation with respect to the motion through the ether, and then rotating it. If the two beams arrived in a tie, for example, constructive interference would make a bright spot at the center of the pattern. But if one beam arrived slightly ahead of the other, destructive interference could make the center dark. In other words, the effect of motion through the ether would be seen in the shift of the interference fringes as the instrument was rotated. To the complete surprise of Michelson and Morley, and just about everyone else, there was no shift at all in the fringes, which means there was no delay. Nothing. No difference at all. The actual experiment was to be done by observing the interference pattern with the interferometer in one orientation with respect to the motion.
Okay, so here's the catch. It's a clever little experiment. It's conceptual, actually. All right, so don't get yourselves confused. The way it is ether, relative to ether, according to the theory. Light moves at the light speed, only relative to ether. Okay. So, Earth is moving on its axis. So, which means that the Earth is rotating on its axis. Also, it's moving relative to the sun. Okay. So, in the direction of the rotation and the motion of the Earth, because the light only moves at the light speed relative to ether. All right, so imagine that the Earth is moving in this direction, rotating in this direction about 1,000 miles per hour. It's also moving in space relative to Earth. So light is moving relative to ether, stationary ether at the light speed. So relative to us in this direction, the light is going to slow down. So the Earth is rotating in this direction. It's also moving in this direction relative to the sun. and the light is moving only relative to ether at the light speed. So which means that while the light is moving in the horizontal direction, it's just going to slow down a little bit. And this, the motion of light in this direction is 90 degrees to the motion of the Earth. So it's just going to go up and down at its regular speed. So this motion is going to be unaffected by the motion of the Earth. So what that means is this light is going to arrive before this one, and it's going to cause an interference pattern on the screen. The interference pattern, instead of getting a constructive interference pattern, may end up getting a destructive interference pattern. That's what it means. All right, so that's what physicists were hoping for. All right, so the Earth is going in this direction, and the light is traveling at the light speed relative to ether. We're also moving relative to ether. So in this direction, the light is going to slow down, and then when it gets bounced back, it's going to speed up, obviously, because we're also moving relative to ether. In this direction, the speed of light is not going to change. So they just measure the distances just so that when the light wave from this mirror and that mirror arrived on the screen, the difference in the path lengths would be multiples of half a wavelength. So which means that we would get a destructive interference pattern on the screen. So when they repeated the experiment, though, they realized that there's no difference in wavelengths, right? Because they end up getting a constructive interference pattern. So they go, this doesn't make sense. So they kept changing the angles and repeating the experiment. No matter how many times they repeated the experiment, it looked like
If the two
beams were arriving at.
beams arrived in a tie, for example, constructive interference would make a bright spot
All right, so they noticed that they kept getting constructive interference
at the
patterns.
center of the path. Surprise of Michelson and Morley through the ether could be seen in the shift of the interference fringes as the instrument was rotated. To the complete surprise of Michelson and Morley, and just about everyone else, there was no shift at all in the fringes, which means there was no delay. Nothing. No difference at all.
So what does it mean? That means that there's no ether, guys. There's absolutely no ether. All right, so relative to ether, the light should travel at the light speed. And if there's ether, you should get a destructive interference pattern on the screen. And because only relative to ether, the light can move at the light speed.
No matter how they varied the experiment, summer or winter, night or day, the result was the same. Light apparently travels at the same speed in all directions, in complete disagreement with the idea of Earth moving through the ether. For the next 50 years, numerous physicists repeated the Michelson-Morley experiment with ever-increasing precision and sophistication, in the vain hope of finding some mistake in that perplexing conclusion. But even in 1887, the facts were clear. The experiment had failed to detect the ether.
What does it mean? Which means that light moves at the light speed. Relative to you, relative to that point P that you were looking at, relative to that point on that paper, on Maxwell's paper, even if that point is moving at the light speed. What that means is relative to you, the light always moves at the light speed. I've been telling you guys forever, ever since the first day on, those of you guys who are taking physics with me the second time around, I've been telling you that your common sense is no substitute for education. Your common sense is completely useless in reality, guys. And all of a sudden you realize that this is the end of common sense in physics. Light moves at the light speed relative to you regardless of your motion. What does it even mean? That's like just about the most nonsensical discover that you can come up with on your own, because your mind just does not even grasp it. We're not even in modern physics yet. Your mind is like, wow, all of a sudden you go, I don't understand. Of course you don't understand. No one does, with the exception of Einstein. Einstein, he's 16, he's looking at it. He's a high school kid. He's looking at it. He's looking at Maxwell's equations. He sees right through the bullshit. He goes, ether? I don't think so. As far as he was concerned, it was nonsensical that there might be ether. As far as he was concerned, space was empty. It's a vacuum. Somehow magically the light travels at the light speed. Relative to that point P, relative to that point, light travels at the light speed. His question is, what if that point is also traveling at the light speed? Then what? Would I be able to see my reflection? And all of a sudden you got your answer. The answer is, of course. Regardless of your motion, the light has to travel at the light speed, relative to you and relative to you only. Kind of like become the center of the universe. This finding is so mind-boggling that physicists could not wrap their heads around it. It's just so bizarre, because if there's no ether, if light is away, what the hell is it disturbing? For it to be able to travel at the light speed. And what's the meaning of, wait a minute, light traveling at the light speed relative to you? I mean, if you're traveling at the light speed, how's that even possible?
In 1892, the Irish physicist G.F. Fitzgerald suggested that the size of one arm of the Michelson and Morley interferometer
And all of them, the physicists, their minds go into
might have somehow contracted. How much it contracted.
their minds go into hyperdrive because they go, wait a minute, this is weird. I wonder if the instruments are kind of shrinking in the direction of motion, some kind of space, and something is happening. They try to come up with mathematical explanations in order to solve this problem.
He said, depended on its velocity. To most physicists, Fitzgerald's contraction sounded absurd. But not to Europe's most distinguished physicist, H.A. Lorentz.
Lorentz is going to come up with his transformations to explain. He's still thinking, well, you know, the ether is there. The reason why we're not perceiving it is somehow the Earth is contracting in the direction of motion.
He worked out a quantitative model to explain the phenomenon, and in the process, developed mathematical expressions that would change the face of physics.
Except Einstein is going to grab his equations and interpret it completely differently, thus coming up with his own theory of relativity, and that's going to become the final and the greatest theory in classical physics, and will take us right into modern physics. It's weird.
They came to be called the Lorentz transformations. In 1899, the great French mathematician Henri Poincaré examined the results obtained by Michelson and Morley. He offered a general explanation, calling it the principle of relativity. The idea behind it was that absolute motion will never be detected in the laboratory. There must arise an entirely new kind of dynamics, he said. Poincaré was right. An entirely new kind of dynamics would arise, but the principle of relativity, which would be its cornerstone, was far from new. It went back at least as far as Galileo Galilei. Galileo had said that an object in motion would tend to remain in that same state of uniform motion. That was the law of inertia. It was correct because in its own frame of reference, every state of uniform motion was, in reality, a state of rest. In other words, Galileo understood not only the law of inertia, but also the reason it was true. There is no difference at all between being at rest and being in uniform motion. For nearly 50 years after his first interferometer, he lived on, measuring the speed of light with ever-increasing precision, measuring the diameter of a star for the first time ever, and even admitting, finally, that his interferometer experiment had provided the verification of Albert Einstein's theory of relativity.
To these was the measurement of the velocity of light. The second, the measurement of the diameter of a star. And the third was a test of the Einstein theory of relativity.
Michelson won the respect of the scientific community, the friendship of Albert Einstein, and became the first American to win the Nobel Prize. But to the end of his days, he never fully accepted the implications of his famous experiment.
He went to his way of thinking that Einstein was wrong, ether existed, and he could never come up with a sophisticated enough experiment to prove the existence of ether. And he thought that sooner or later, the physicists were going to come up with a sophisticated enough experiment to prove him right. Guess what, guys? There's no such thing as ether. Einstein was right. There's no ether. He wanted to rescue the sense of his common sense. All right? It just so happens nature does not care much about our common sense. If there's no ether, then what is the medium that the light is disturbing? I mean, it's a wave, we prove that. And we also know that the wave requires a medium to disturb so that it can travel at the light speed. But there's no medium that the light can disturb. So how is it that it's able to travel at the light speed? Now that question took a while to answer. These questions took literally a lifetime to answer, usually 50, 60, 70 years. Eventually, physicists settled on the idea that the light is a self-propagating field. All right, so there's no medium that it disturbs. Any variation of the strength of the electric field creates the magnetic field component. Any variation of the strength of the magnetic field component creates the electric field component. So it becomes a self-propagating field in essence, so that it can travel at the light speed through the vacuum of space. So that's the explanation that we have to that.
We often teach physics in a historical way. The purpose, of course, is not to teach history, but to teach physics. And so, very often, we redesign the history. We tell you not what really happened, but what should have happened. Well, I suppose that it serves some pedagogical purpose to do that. So let me tell you what should have happened at this point. There should have been a patent clerk in Switzerland named Albert Einstein, who should have said, look, the Michelson-Morley experiment compels us to do two things. One is to restore the principle of relativity. And the other one is to believe that the speed of light will be the same to all observers, regardless of their state of motion. And from those two fundamental postulates follow all the astonishing results of the theory of relativity. Now let me tell you what the facts were. One is that Michelson, of course, never for the rest of his life believed the results of his own experiment. But the other one is that Einstein not only didn't base his theory on the Michelson-Morley experiment, but he later claimed that when he wrote his famous paper in 1905, he had never even heard of the Michelson-Morley experiment. I will see how that was possible when we go on with this next time.
He was a kid. He was 16 years old. He was enamored by Maxwell, obviously. He was studying Maxwell's paper. And all of a sudden, I mean, being a genius that he was, he's thinking, wait a minute, what if that point, relative to which the light moves at the light speed, but what if that point is also moving at the light speed? That one. Because to him, it didn't make sense that the empty space would have some kind of it would be filled with a theoretical substance like ether, which is supposed to be infinitely rigid. At the same time, it's going to have almost zero density. I mean, what is that? What is that? It boggles the mind that intelligent people will believe in something like that. All right, so what do we know? Newton comes up with the particle theory. Huygens comes up with the wave theory of light. Young's double slit experiment proves that the light is a wave. Maxwell comes up with the electromagnetic wave theorem, or theory of electromagnetic waves, according to which light is an electromagnetic wave. He proposes a medium for it to travel in, which is ether. He actually borrows the concept from Huygens, this guy. And then there are Michelson-Morley experiments that proves that there's no ether. There's no absolute space, no stationary reference frame. Everything in the universe moves relative to everything else. That's what it means. So when you're dealing with light speed, the question becomes relative to what? Relative to any observer, the light travels at the light speed. That's what it means. Speed of light is an invariant, which means that it doesn't change. Regardless of how fast you may be traveling, light is always going to travel at the light speed relative to you. That's what it means. If I'm traveling at 60 miles per hour, relative to me, light still travels at the light speed. I can see myself in the mirror. I'm on an airplane moving at 450 miles per hour. I look into the mirror. I see myself immediately because light from my face still travels to the mirror at the light speed. So the question becomes, what if I'm traveling at the light speed? Would light still be able to travel at the light speed relative to me? And all of a sudden, if Michael-Morley experiment is correct, and then you realize that Einstein had a valid question, which means that the light should still travel at the light speed relative to you, which means that you should still be able to see your reflection. But the question becomes, while I'm traveling at the light speed relative to you, if light is moving at the light speed relative to me, shouldn't my light be traveling at double the light speed relative to you? Well, according to this finding, the same light should still travel at the light speed relative to you. So how's that possible? Why is it that the light in my reference frame, while I'm traveling at the light speed, is traveling at the light speed relative to me and traveling at the same light speed relative to you when you are here on the Earth reference frame? All right, at that point, notice that the logic starts to break down. And that's the reason why Einstein had to think about it for 10 years. And then we'll discuss the solution either this week. All right, now let's talk about the planets. All right, so evidently at the time of my preparation of this PowerPoint, this is probably 15 years ago originally. They discovered like 500 planets back then. Now we got thousands upon thousands Earth-like planets have been discovered. All right, so the problem is planets only reflect light, so they're not the sources of light, so you can't see them directly. They usually are lost in the glare of the stars that they belong to. Okay, so how do we detect planets if that's the case? All right, so technology moved on. Originally, here's what we used to do. Remember the action and reaction forces being equal to each other? All right, so the force of gravity extends all the way out to the moon. The moon applies the same force back on the Earth. All right, so as a result, what happens? The moon orbits the Earth, and because the Earth experiences the same gravitational pull, it's much larger in mass than the moon. It does a small counter orbit. So which means that the Earth is not stationary. They will be moving relative to a common center mass between these two. So the Earth does a small counter orbit. Imagine that this is the star that you're trying to see that you won't be able to, obviously. And this is the star. No, this is the planet. This is the star. This is the planet that you want to see, and this is the star that this planet belongs to. Star is the light of source. It's the source of light, obviously. And because of the glare of this light, you won't be able to see the planet. But if there's a planet attached to the star, you should be able to detect the wobble of the star. All right. Any star that has planets will wobble this way and that way. And how do we know that it's wobbling? How can we even detect the wobble if the star is, say, 2 light years away, 10 light years away, 50 light years away? You can. What happens is because the star is wobbling, the color of the light is going to shift from red to the blue, from blue to the red end of the spectrum.
She sees the speed of a star
So you won't be able to see the stars. You won't be able to see the planet itself, but you can detect the wobble in the star.
change with a clear rhythm. She'll know the star has an orbiting planet. Just as two rollerbladers spin around each other, a planet and its star are in mutual orbit. Gravity works in both directions, so that even a small object like a planet will cause a much larger object like a star to wobble. Such a wobble in a distant star would be indirect evidence of a planet. But how do you see the wobble of a star? Just as sound rises in pitch as its source travels toward us, and drops as it moves away, so light shifts in color as a star wobbles. For years, Fisher and her collaborators have been looking at a star called Gliese 876. The star's color has been shifting. Fisher is hopeful she's seeing a wobble caused by a planet, but she isn't yet convinced. Fisher isn't the only researcher to look for rhythmic star motion. In 1994, another team was searching the constellation Pegasus. Back then, no one had ever found a planet around a distant shining star. Astronomer Didier Queloz thought he saw a star wobbling because of a planet. If Queloz was wrong, his credibility and his young career might be destroyed.
I realized that it was highly risky if the data turned out to be wrong and a mistake. It would have been very bad for me.
The technical challenges were reason enough for caution. Earth zooms through space, but stars move slowly.
It's as if you were in a rocket and trying to monitor the speed of ants on the ground.
Queloz had to figure out what his measurements meant. He first convinced himself he wasn't seeing sunspots on his star, called 51 Peg, rather than star motion. He next made sure the star wasn't quivering like a serving of cosmic jello, rather than moving back and forth. Finally, Queloz knew what 51 Peg wasn't. Now he had to take the leap to say what it was. Didier Queloz's star was wobbling. After careful study, only one explanation made sense. An unseen planet must be moving 51 Peg. Queloz had discovered the first planet orbiting a distant shining star, but others were skeptical.
When we announced 51 Peg, I think that maybe only 10% of the people believe we had a planet.
Scientists never thought such a world could exist. It was a planet 140 times the mass of Earth, and it wasn't supposed to orbit this close to its star, according to planetary theory. Queloz's world is an unlikely sight for life. It whips around 51 Peg every 4 days. The temperature is 1,500 degrees Fahrenheit, so hot that the metal nickel vaporizes, perhaps adding a blue glow to the fiery atmosphere. After Didier Queloz's discovery, other planet hunters knew they were on the right track. Now more than ever, Deborah Fisher and co-workers were eager to find their own world. If her star is really wobbling because of a planet, she should be able to predict the star's next move. Fisher began with the star speeds she had measured. She then used these measurements to make predictions of what her star would do next. As she observed her star again on a series of nights, each of her predictions came true. Deborah Fisher had found her first planet.
It was a very powerful feeling to make a prediction and have a star obey my, my command.
Fisher's planet is a ball of gas nearly 700 times the mass of Earth. Her planet swings in a wild orbit that takes it from burning proximity to the star to a freezing distance. Angel's novel two-eyed telescope.
All right, so when this planet is moving up towards us, there's going to be a shift in color towards the blue end because the wavelengths will become shorter. When the planet is moving away from us, okay, I said it wrong. When the star is moving towards us, there's going to be a shift in color towards the red end, no, towards the blue end, because the wavelengths will become shorter. When the star is moving away from us, the wavelengths will get longer, which means that there's going to be a shift in color towards the red end. All right, so that's the original way of looking for these planets belonging to stars.
Maybe the first to analyze.
And then they came up with this telescope.
Directly the faint light of an alien planet. The two mirrors will be yoked together to create history's biggest pair of binoculars. Each mirror will have a slightly different view of the star. The light waves from these two vantage points will be combined to reveal a distant planet's light.
Well, the difficulty with trying to see planets around stars is that they can be a million or even a billion times fainter than a star. So any kind of glare from the star spoils your view of the planet. There's a trick to get rid of the starlight and leave the planet light there. And what you can do is combine the waves from the two mirrors so that the crests from the wave from one mirror come at the same time as the troughs from the other. When you add those together, the starlight cancels. So that way you can make a star thousands or tens of thousands of times fainter and leave the planet so you can detect it.
Angels.
All right, so the whole idea is they have these two mirror telescopes, and then they're trying to create an interference pattern between the mirrors, light reflected between these two mirrors. So the starlight could be caused to interfere destructively. As a result, what happens, the star is going to become dimmer, so you could see the planet in front of it or around it. That's the whole idea. So given the fact that we discovered thousands upon Earth-like planets, so what are the chances that there's life elsewhere in the universe? All right, that's pretty good in essence. And we always thought that there was pretty good chance that if life existed here on Earth, chances are pretty good that it probably exists elsewhere in the universe. The question always was, would there be advanced enough creatures elsewhere in the universe, intelligent enough, to have technologies that would allow them to actually travel in space and visit us? And so the answer to that question was maybe or why not for the most part. But a lot of the skepticism was about, let's pretend that there are civilizations out there, creatures out there who are just as intelligent as we. All right, so is it possible that they could actually travel in space? And given the fact that the near Earth-like planets that we discovered a few light years away, is it possible for them to be able to travel at the light speed or near the light speed to travel here? So just because we cannot do it does not mean that it cannot be done. So if the answer is yes, is there any sort of evidence that we're being visited by space aliens? All right, so now let's take a look at it from our perspective. Okay, number one, let's talk about the way we travel in space. We still use the chemical-based propulsion units systems. And so the question is, how does that work?
Space begins at the edge of the Earth's atmosphere, 50 miles straight up. But the shuttle orbits at an altitude of about 180 miles. How does it get up there? Space travel is all based upon Isaac Newton's third law of motion. This fundamental principle of rocket motion is 300 years old, and we've enlisted rocket scientist Wayne Lee to explain it.
Believe it or not, you don't have to be a rocket scientist to understand how a rocket works. This balloon here is essentially a rocket that's powered by compressed air. What happens is that when the air rushes out, it propels the balloon forward up the string. This is exactly Newton's third law at work. When the balloon throws the air overboard, the opposite reaction propels the balloon up the string.
Wayne Lee put on ice skates for the first time in 15 years, all in the name of science.
Newton's third law says that for every action, there is an equal and opposite reaction. So simply stated, that says that I cannot push on something without that something pushing back on me with equal strength. And so as in this example here shows you how rockets work. You can imagine that I'm the rocket, and my partner here is the rocket fuel. I am pushing off on the rocket fuel, and that propels me in the other direction.
All right, so the propulsion, chemical propulsion, works on Newton's third law. Action forces acting on the fuel. The reaction is forces acting on the rocket. That's it. So that's how we accelerate in space. With this sort of technology, you can get up to like 25,000 miles per hour, maybe about 30,000 miles per hour, and that's it. And if you're trying to travel long distances, it would take lifetimes to get to a nearest Earth-like planet. It may take 1,000 years. It may take 1,000,000 years. All right, so that sort of technology is not going to be able to get us anywhere in space, in essence. All right, so just because we cannot do it does not mean that it cannot be done, obviously. All right, so if it is doable, if there are creatures out there who are just as intelligent as we, and if they have been playing this game called technology for longer than we have been playing it, chances are pretty good that they can do it. So the question is there any evidence? All right, guys, the technology that we have today, 100 years ago, this sort of stuff wasn't even possible in the minds of a lot of people. I mean, are you kidding? I mean, we can televise things live. You can watch events live on TV. This is, in the minds of people 100 years ago, this sort of stuff would not be possible. Flights would not be possible. Forget about going to the moon. And look at the advances that we made within the past 20 years. Look at the advances that we made within the past 10 years. Imagine that we keep playing this game for the next 1,000 years. 1,000 years from now, when people look back, we will look so primitive in the eyes of those people. The technology is going to be 1 trillion times superior to what we have today. We won't be any more intelligent. You don't need to be any more intelligent. The technology, the science is going to keep advancing. That's what it means. So if there's a civilization out there, elsewhere in the universe, done by creatures who are just as intelligent as we, except if they have been playing this game for 1,000 years longer than we have been, 1,000,000 years longer than we have been. Technologically, they would be much, much more superior to us in that sense. All right, so if that's the case, if we're being visited, the question is there any evidence for that sort of stuff? All right, so let's take a look. Where would you find evidence for something like that? All right, so this is in our project done by one of my art students. And this is a simulation project done on 3D Max. This is like more than 20 years ago. This guy is a professional now. And then so he decided to do a simulation. The way the simulation is done, it's not difference between animation and simulation is you create these objects that you look at. Instead of doing an animation, what you do, you go in there and you attach formulas to these in every single term that you have. So this is one of the things that I used to teach the animation students. So instead of spending days trying to animate something, if there's mechanical motion or something, you would attach formulas and make it look extremely realistic. So this guy comes up to me, this is his final project, and then all of a sudden we were doing the simulation on it, and then boom, immediately you know something is wrong. What's wrong is this ball. It's accelerating, all right? Unless it's got some kind of a propulsion unit that we cannot see, it cannot accelerate, which means that it's able to generate an external force on itself, which means that it's got some kind of a propulsion system that we don't see. And immediately your eye just catches it. Okay, so what that means is when it was entering the formula, he ended up entering the time term twice. So time being just t, single time, it became time squared. And obviously he's entering the same formula for every single the ball that he created. And here he must have gotten careless. He ended up entering the time twice. And all of a sudden it creates an acceleration on that. So he goes, oh, he said, oh, let me just go correct it. I said, no, don't, because I like it the way it is. The thing I like it about it is all of a sudden this got some kind of a propulsion system. All right, so it's able to generate an external force on itself. It makes contact here and then boom, something.
Your audio is a little wonky right now.
All right, so all right, guys, this is. Okay, is it better?
Yes.
All right, all of a sudden, this is not following the laws of physics. Okay, so it's doing something, and then obviously in real life, you wouldn't see something like that accelerating on its own, unless it's got some kind of a propulsion system that you don't detect. All right, so this brings us to a couple of things that we're going to look at. Let's check to see if there's any signs that we're being visited. Okay, guys. All right, let me just get this out of the way. All right, from my there are people who are firm believers on this sort of stuff. All right, my dad is one of them, obviously. I grew up listening to stories like that. My dad probably read just about every single book on this subject matter. You'll see shows on TV. Discovery Channel used to have plenty. The History Channel now has plenty of shows. People talk about being abducted, this and that. And if you're a believer, you will believe in just about everything. And if you're a skeptic, you're not going to believe in anything. In a sense that if somebody sees something and takes a picture of it, today we'll say it's Photoshop. If you see something and talk about it, we'll say, oh, it's just an illusion. It's optical illusion. A bunch of people look at the same thing and they see the same thing, and then that's called mass illusion. All right. You capture it on video. It's called, people say that it's doctored. Obviously, we got the technology today. You could just special effect just about anything you want. But you know, you can trust the government, right? Well, you know, that's not true. But NASA, I gotta tell you, there's no reason for NASA to lie. If you ignore the Challenger disaster and the Columbia disaster.
We're seeing now is actual footage
and if you ignore the cover-up.
By NASA cameras from that shuttle mission. Watch the top of your screen. Note the object that moves from right to left. Two mysterious flashes, and it makes an immediate 135-degree turn and accelerates. This is followed by a strange streak of light, which seems to narrowly miss the unknown object.
All right, so this is a live footage from NASA, I think 1992 or something. And what you guys are looking at, these are known as ice particles. They're byproducts of a shuttle mission. All right, that's a clean and politically correct way of saying, you know, you have to go to the bathroom, so what do you have? You got crap and you got piss. They're not going to carry that stuff with you. They just put it outside. Space is really cold. It's about 4 Kelvin, negative 294 Fahrenheit, negative temperature. So eventually, things will freeze up into these ice particles that you're looking at. All right, so because of inertia, they're going to be moving with you in the same direction at the same speed, 17,500 miles per hour. All right, so what you guys are looking at is a byproduct of a shuttle mission. Everything should be moving in the same direction at the same speed forever and ever and ever, and that's what it is. Motion under the influence of gravity. All right, so they are just announcing this thing just for no reason at all. It stops and then changes direction. All right, so that little thing catches somebody's attention for some reason. And the person who notices this is someone who's working on the Star Wars project. And he's not just someone, this guy is a physicist. He's a physics professor, physics PhD. And he goes, wait a minute, did that thing just stop in space and change direction and accelerate in this direction? Ice particles can't do that. All right. I mean, you're going at 17,500 miles per hour. How do you stop in space briefly, and then how do you just accelerate in space in that direction without an external force acting? I mean, if I'm somehow driving my super Ford Tempo at 17,500 miles per hour, if I wanted to stop, I would have to put the brakes on, and then hopefully within an hour I will come to a stop. You just put the brakes on within an hour, maybe 10, 15 minutes. The car will catch fire, for God's sake. Right? You can't just put the brakes on in space like that and come to a stop from 17,500 miles per hour and then accelerate like that without any sort of advanced propulsion system. Now, we don't have that kind of propulsion system that could allow you to come to a complete stop in space within a short enough distance like that and then be able to accelerate. Chinese certainly don't have it because they work with the technology that they are capable of stealing from us. Usually a lot of it is junk. Russians, give me a break. All right. Technologically, they're not comparable to the United States. All right. Even they know. So if it's not us, if it's not Russians, if it's not Chinese, then who? All right, so where are we? How's that possible? All of a sudden, this becomes 1990. All right, so there are 3-4 cases that physicists take seriously, according to Wikipedia, and this is one of them that I was able to find.
We're better to look for alien craft visiting our planet. In September of 1991, the Space Shuttle Discovery captured an unidentified object on film. What you're seeing now is actual footage shot by NASA cameras from that shuttle mission. Watch the top of your screen. Note the object that moves from right to left. 2 mysterious flashes, and it makes an immediate 135-degree turn and accelerates. This is followed by a strange streak of light, which seems to narrowly miss the unknown object. This dramatic footage has been in dispute since it was shot.
I studied it extensively over maybe a 2-year period at least.
University of Nebraska physicist Jack Asher worked for nearly 10 years in the research and development of a Star Wars defense system for the upper atmosphere. His quantitative analysis of the NASA footage concludes that the UFO cannot be explained as a natural phenomenon.
It's clearly above the atmospheric air glow of the Earth. It maneuvers, it changes direction, it accelerates, and so the only thing really left is spacecraft.
Others think this object is simply a small ice particle floating a few feet from the shuttle. Ice particles are a common waste product of the numerous shuttles that have orbited Earth. But Kasha is convinced NASA has recorded strong evidence of a large, intelligently controlled alien space vehicle.
One of the very strange things that happens is that the main object actually stops and sits there for half a second before it accelerates back up to the right. An ice particle could not do that. If they're not ice particles, you don't have too many other options. They're not space junk, they're not satellites, they're not meteors, because those objects don't change direction.
UFO was miles from the shuttle, well out of range from a thrust of firing, and that it was moving at an incredible speed.
If the object is as close as 10 miles, it went from 0 to 2,500 miles an hour in 1 second. And that's an acceleration of more than 100 Gs, which would kill a human pilot. And the technology we're looking at is just quantum leaps beyond anything we have on the Earth.
Okay, cute. Not everyone is convinced that his explanation is valid. That's always the case, because there are people who, regardless of what you say, they're not going to believe in it. And some people are, some people will go along with it. This physics is solid. You can't accelerate in space without a propulsion system. And this appears, it looks like an ice particle. It doesn't need to be depending upon the distances. This thing appears to be accelerating at well. Obviously, technology, he's suggesting that we don't have that kind of technology, which we don't. Okay, so that makes sense. If his interpretation is correct, then it's got to be some kind of a alien spacecraft. That's the interpretation that he has. A lot of people who are not as knowledgeable about physics, and those people will disagree with them, will say, hey, wait a minute, if we're being visited, why are we just looking at these things that look like ice particles? Why not make your presence known, for God's sake? All right, you're already here. All right, if that's the case, just say hello. All right, just make yourself visible. Just communicate with us. Just open up the channels. Let's have an interesting communication, and let's just establish some kind of communication, because we want to communicate with these creatures if there are creatures out there. And that's the thinking that some of these people have. And these people who usually think like this tend to be academics. From the perspective of, I mean, just guys, look at us. We don't even trust Canadians. We have a border between the United States and Canada, and the Canadians are the closest thing to us. All right, human beings are just about the most dangerous animals that you can imagine. We tend to be tribalistic. All right, and we don't trust people who don't look like us and who have different religions, who have different nationalities, this and that. This is the way it's been for thousands upon thousands of years. And the United States is a bit of an anomaly, because most of you guys, born and raised in the United States in these awesome cities or suburbs or whatever, and your understanding of reality is a little bit skewed. This is not the way it is elsewhere on Earth, for example. And if you don't know what I mean, just go to Syria with an American flag and then just start walking around shouting USA, USA. In no time, somebody's going to do something about it. All right. If you don't have the right skin color, you could be killed elsewhere on Earth. People are extremely, extremely dangerous. And you're thinking, oh, you know, I'm better than that. You may be. But just think about what you ate for breakfast this morning. How was your bacon? All right. For that bacon, an animal was killed who's just as intelligent, and if not more intelligent than your household pets. All right. And animal got killed, which didn't have to be killed. All right. We end up eating animals who are just as intelligent, if not more intelligent than our household pets, not because we're hungry, but because they taste good, guys. I mean, you cannot be any more violent than that. It's absurd. It's absurd. It's beyond absurdity. And most of you guys even don't even realize it because it's part of the common culture. Now, imagine that these creatures come in and they're intelligent enough to know that we're dangerous. What makes us think that they're going to make themselves available for communication? For one thing,
First I was afraid, I was petrified, kept thinking I could never live without you by my side. But then I spent so many nights thinking how you did me wrong, and I grew strong, and I learned how to get along, and so you're back from outer space. I just walked in to find you here with that sad look on your face. But you the one who tried to hurt me with the vibe, and I crumbled. We gotta lay down and die, oh no, not I will survive.
Maybe it is the environment, and maybe they look like fish. What if they look like fish? All right. And you know, at some point, somebody's going to go, oh, well, we know they're intelligent. They're just as intelligent as we are. But I wonder what they taste like. Because killing a space alien is not against the law. Come think of it. You know, something is going to think about it, right? And you know, somebody's going to do it. All right. So maybe they're thinking that they cannot trust us. That's one way of looking at it. There's also a second way of looking at it, guys. If they don't like us, they could do what we've been doing to inferior civilizations. Every time we showed up, we messed things up, especially the Europeans did. All right, just they could be looking at us exactly the way we look at animals. I'm talking about pigs and this and that. We could just as easily become their protein source. All right, they can just set up McDonald's all over the universe, just serving human meat. So this sort of stuff could also be really dangerous.
We're going against the wind. The wind's 120 knots per west. There's a whole fleet of them. Look on the SA. My gosh. We're going against the wind. The wind's 120 knots per west. I'm walking, dude.
All right, so the question becomes, is it possible to travel in space close to light speed? Is it possible to take shortcuts through the space-time continuum? All right, so this sort of stuff is going to take us into modern physics. So we'll keep investigating. All right, so you got the soap bubble. Notice that you have all these iridescent colors. So the question is, where do we get these iridescence on these soap bubbles? This is known as the thin film interference. The person who came up with an explanation for it is a Frenchman. His name is Fresnel, and he was able to explain this by using the wave phenomena. So that's what we will focus on. So here's a picture of Fresnel. All right, so what caused the thin film interference? So you got the incident light, you got air, you got glass, and you got water down below. And so the light is going to get reflected from this boundary into your eye. And then this light gets refracted and gets reflected from this boundary and then gets refracted into your eye. There's going to be an interference pattern between the first light, reflected light, and the second reflected and refracted light. All right. So which means that the interference in your eye is going to be either constructive or destructive. For certain colors, it's going to be constructive. So if that's the case, you will see that color. If it's destructive, that color is going to vanish from this light. All right. Once again, you got the incident light. You will get a reflection from the boundary. And then some of that incident light is going to go through the material. It's going to get refracted and reflected and refracted again. So there's going to be an interference pattern between this light and that light. And certain wavelengths will interfere constructively. So you will see those wavelengths, which means that you will see those colors. And certain wavelengths will interfere destructively. So they will vanish from that. So this is known as the thin film interference. All right. So let's talk about the mechanism of constructive and destructive interference from these waves. All right, so here's the pulse coming from a less dense medium towards the denser medium. So what's going to happen? It's going to get reflected. Reflected pulse is going to be inverted. So when the wave is coming from a less dense into more dense medium, all right, when the reflected pulse is going to be inverted relative to the incident pulse. All right, so you got your transmitted pulse is doing the same thing. So part of the pulse is going to get inverted. So the reflected pulse is going to be inverted relative to the incident pulse. All right, so this happens when you come from a less dense into a more dense medium. Incident light is coming from less dense into a more dense medium. So notice that it gets reflected right at the boundary. When it's reflected, this portion is going to get inverted relative to this. All right, so this becomes an inverted wave. So reflected wave that you're looking at is going to be inverted relative to the incident light. Got it? All right. Now the pulse coming from a more dense into a less dense medium, when reflected, it's still going to be upright. So it's not going to be inverted, it's going to be upright. All right, so when the wave is coming from a more dense to less dense medium, reflected pulse is going to be in phase. It's still going to be upright. That's what it means. All right, so here's the light coming from a more dense into less dense medium, so it gets refracted. All right, so the refracted light, this is the, okay, so, okay, I said it wrong. Okay, more dense to less dense, the reflection is happening right here. Okay, so I said it wrong. Okay. So this light is in the more dense medium, this is less dense. So upon reflection, this light is going to get inverted. No, this is non-inverted light. So this light is going to be non-inverted. And then it gets refracted out. This one is inverted. This one is not inverted. So they will be out of phase with respect to each other by a multiple of a single wavelength. That's what it means. All right, so which means that there's going to be destructive interference between this and that. This one is inverted. This is not inverted. So naturally, this one is inverted. This is not inverted. Naturally, relative to each other, one of them is going to be inverted. The other one is not going to be inverted. All right, so by adjusting the thickness of this material, you can either cause constructive interference, depending upon the thickness of this material, you can either get a constructive or destructive interference pattern in your eye. All right, so when there's an interference between these two waves, depending upon the thickness of this film that you're looking at, whatever this gas is, all right, you will either get a constructive interference or destructive interference between these two light waves. All right, so that's what we're going to be looking at. All right, so this one is inverted, so there's a 180-degree phase change. That's what it means. And this one is non-inverted, so there's no phase change. All right, so this wave is going to be inverted relative to this one. Whether you get a constructive or destructive interference pattern depends on the thickness of this film. That's what it means. So for us to be able to get a destructive interference pattern, remember, light is going to travel this distance twice. This is the thickness of this material. All right, so if you maintain a multiples of a single wavelength within this thickness of this, twice the thickness of this material, you will get a destructive interference pattern. All right, so this light is going to travel this distance, this thickness twice within that distance. If the wavelength difference between these two is multiples of a single wavelength, then you will get a destructive interference pattern. That's what it means. So to retain the destructive interference pattern, in this case, it's a destructive interference pattern. You just have to, okay, so the wavelength is going to become shorter. What that means is you need to keep difference in lengths between these two waves has to be multiples of a single wavelength divided by the index of refraction of that pattern that you're looking at. If you want to cause a destructive interference pattern, the constructive interference pattern is going to happen only if the difference between wavelengths is multiples of half a wavelength. All right. All right, so what's the meaning of that? The meaning of that is the following. All right, so naturally, this one is inverted relative to this one. Okay, forget that. Let's take a look at this case first. Okay, this is not the same as the previous case. Less dense to more dense. Okay, so this way becomes inverted. All right, less dense to more dense. This becomes inverted as well. Naturally, both of them are going to be in phase. All right, naturally, you end up getting a constructive interference pattern. And also, it depends on the thickness of the material. If twice the thickness of this material is multiples of a single wavelength, you retain a destructive interference. All right, and you retain a constructive interference between these two waves. And I'm not talking to that. All right, we're looking at this bird. Obviously, you end up seeing all these iridescent colors that you're looking at, and this happens because of the thin film interference. The colors that you see are the colors that are still visible because of the constructive interference. All right, the colors that vanish are the ones that you don't see. Those vanish because of the destructive interference. All right, so the colors that you see are a demonstration of the interference pattern. It's in film, so that's the best ever. The E is the best answer. All right, so the interference colors in a soap bubble is the evidence that number one, it's going to have two reflecting surfaces, top and the bottom, and it's also going to be thin. So I would say it should be C in this case because it's a thin film interference, not because it's got two reflecting surfaces. It also has to be thin. So B, C, that's not for that one. All right, let's take a look at a few problems just to make the point clear. Once again, the mathematics of this is straightforward. It's not that complicated. All right, so you got the incident lights. So we got a colored thin film of gasoline. So the gasoline is located here. Index of refraction of air is going to be 1. Gasoline is going to be 1.4. And then the gasoline is on top of water. So we have a thin film of gasoline. And obviously, if you're looking at it, you're going to see these iridescent colors, different colors. All right. So we got the gasoline floating on a puddle of water. We got the sunlight falling almost perpendicular straight on. All right, so whatever this angle is, it's fairly small. And then the light is going to get reflected into your eyes from the thin film. All right, so there's a clarification that says this, although the sunlight is white, which means that it's going to have all the colors that you see, you will end up seeing the film has a yellow hue, so it's going to end up looking yellowish because destructive interference is going to eliminate the blue color. So the blue color, obviously blue color, there's going to be a reflection from here. Blue color is going to be inverted here, and it's going to be non-inverted here. And then within the thickness of this film, you end up getting a destructive interference as a result. The blue vanishes, and then you see yellow. That's what it means. That's also the reason why, because of scattering, the sky is blue, and then the sun looks yellow. It's exactly the same reason. All right, so if the refractive indices are given, so air, you got the water, and you got the gasoline, whatever. So those are the numbers. And then repeat the same. All right, so what are we looking for? Determine the minimum non-zero thickness of the film that causes that destructive interference pattern for the blue one. All right, so non-zero thickness. Okay. All right. All right, so this one is inverted and this one is not. Okay, so when it's inverted, there's going to be a path difference between these two. So they're going to be, the path difference is going to be multiples of half a wavelength. And that's what it means. So the interference is going to be half a wavelength that you're looking at. Let's go back. All right, so this is the one that we're looking at. So which means that this gets inverted. Phase angle is going to be pi, but don't worry about that. So which means that this is going to be inverted relative to this one. All right, so notice that this is going to be out of, I'm going to say out of phase. I don't know how else to describe that because in physics, we normally would talk about phase angles, but it makes sense to talk about the difference in path lengths because it's much more intuitive from non-physicist perspective. So when this is the difference between these two path lengths between 1 and 2 is going to be multiples of half a wavelength naturally. So you need to keep that difference in path lengths multiples of half a wavelength within the thickness of this film when you actually travel this distance twice. So here's the wavelength of blue. So what is the minimum non-zero thickness that's going to retain this destructive interference pattern? All right, so both of them are inverted relative to each other. So we want to actually retain the destructive interference pattern within this thickness. So what is the non-zero minimum thickness for this? All right, so M has to be 1 that we're looking at. All right, so within the gasoline itself, the wavelength is going to become shorter by index of refraction. And naturally, between these two waves, we have a destructive interference pattern. Anyway, we are just trying to retain it. So within this thickness, twice the thickness of the thin film, you want to retain the path difference of a single wavelength between those two waves. All right, this becomes the formula. The only thing we have to do is just plug the numbers in at this point. So M1 is going to give you first order destructive interference pattern, non-zero destructive interference pattern. All right. So we know the wavelength of blue, and we know the index of refraction for the gasoline, which was 1.4. So it's going to give you a number in terms of nanometers. So that's it. All right. All right. So instead of water, what if it's glass? All right. So this one is air. This is going to be gasoline. This is going to be glass. All right, so we end up getting a reflection between air and gas, and this one is going to be inverted. All right, so inverted meaning that the path difference between this and that is going to be half a wavelength. This gets refracted, and then it's hitting the boundary between these two surfaces. This one is denser. This one is going to be inverted relative to this one, so which means that the path difference between these two waves is going to be half a wavelength as well. All right, so this is half a wavelength off. This one is half a wavelength off. So relative to each other, there's no phase difference. All right, the path differences will be the multiples of a single wavelength in this case. So you will get a constructive interference pattern between these two. So what is the minimum required? So which means that both of them are in phase at this point. So if you want to make the color blue vanish, the thickness of this film has to be multiples of half a wavelength. So we're trying to cause it, we're looking for a destructive interference. So what is the non-zero minimal thickness that's going to cause a destructive interference pattern? So you end up seeing the color yellow instead. So that's the reason why within twice this thickness, you need to have multiples of half a wavelength in essence. Right, so this becomes the formula for that. Solve for T. And for this one, M, you could make it 0 if you wanted to. It makes no difference. All right, so M0 is going to give you the 0th order destructive interference. And plug the numbers. And so that becomes the thickness.
In recent.
All right, so when they were designing these mirrors, how did they know that they had the perfect shape for that mirror? Which deformed in space because it was in free fall. And that's okay, guys. Here's how you know. So the optical flatness is what they look at. All right, and obviously, if you're looking for something concave or whatever, you're going to end up seeing these interference patterns. All right, and look at this. You end up getting these interference patterns. All right, this is almost perfectly concave, obviously not 100%, which means that you have to keep shaping it. This is not so much. All right, so whenever they're testing it, they check to see if you get these perfectly circular rings. These are known as Newtonian rings in essence, or Newton's rings. And if they're perfectly circular, then you're done with your job. All right, Newton's rings are a demonstration of interference. All right, so how do you make an aircraft radar invisible? Stealth.
Engineers first came up with a new stealthy shape. They used some clever math to remove any square panels and 45-degree angles, which dramatically reflect radar. As a result, they designed a multifaceted diamond-shaped airplane with radical zigzag edges around doors and windows to reduce the RCS, or radar cross-section.
Radar cross-section is really the amount of energy that's reflected back from the aircraft to a radar on the ground that's looking for it.
Another way to reduce an aircraft's radar cross-section is by applying radar-absorbing material, or RAM. It's a secret recipe of electromagnetic materials which absorb or redirect radar energy coming from ground-based stations or other planes. A computer sprays on the coating, which absorbs the high frequencies directed at the plane, while the radar-absorbing structure absorbs lower frequencies. Shaping and coating reduce the F-117's radar cross-section by 85%.
Okay, so how does the radar absorption happen? Let's focus on that one. All right, so this is problem number 8. We're trying to make an airplane radar invisible. And we're using an anti-reflective polymer for that. It's a polymer paint. And assuming that the radar is being emitted at a given wavelength, obviously there's a bit of an assumption here. So this solution is very sensitive to the assumptions that we're making. All right, so the radar site is using this wavelength. It's 3 centimeters long. Index of refraction of the polymer is given to 1.5. And then obviously you got this polymer paint. The computer is gonna actually put the paint on, and so what should be the thickness of this paint so that this radar is 100% absorbed into the material. So that's what we're gonna do. Physics of it is straightforward. I'm not sure what kind of paint that they use. This polymer is just a suggestion, obviously. It can be done. I'm not sure how readily you can find this sort of paint, because if it's possible, I would probably want this on my car so that I can travel 500 miles per hour without getting a ticket. All right, how does this work? So I'm gonna change things around a little bit. I'm gonna use the same setup. So what do we have? So we got the incoming radiation, so we got its wavelengths. We got the polymer, so paint is gonna be right here. All right, so index of refraction of this is gonna be 1.5. Index of refraction of metal is gonna be infinitely large because the light is not gonna penetrate through it. Obviously, that's what it means. So you will end up getting the reflection from that. All right, so this one, the polymer is denser than air, so reflected light is going to be inverted. And metal is obviously has an index of refraction which is infinitely larger than polymer. So once again, this is going to be inverted. So relative to each other, there's no phase difference between these two, so they're perfectly in phase. Which means that we're getting a constructive interference between these two at this point. All right, so we can adjust the thickness of the polymer just so that emerging light is going to be out of phase relative to this one. So this one is going to be inverted relative to this one, in essence. So what would that thickness be? So here's the incoming radar. Here's the index of refraction of polymer. What is the thickness of the material so that emerging light is going to be out of phase relative to this body, relative to this wave by multiples of half a wavelength in essence. All right, so which means that this, within the thickness of this material, the double the thickness of this material needs to be multiples of half a wavelength. That's what it means. And so this is the formula that we end up using. And so what is the minimum thickness which is required so that the arc-on wave is going to be inverted relative to the reflected ray? That's what we're looking for. So you can take m to be 0, solve for t. All right, so this has to be the thickness of the paint that's going to be put on the aircraft. And it needs to be computerized, obviously, because this is an exact measurement. All right, so which means that the radar is going to get absorbed into the material and you're not going to be able to see it because of the thin film interference.